This is more of the wind loading variety. This was Eagle Creek headwall, very small amount of precipitation in early February, but followed by some loading winds was enough to create these avalanches at the headwall of Eagle Creek, which is just north of Ketchum. So that's where we're at right now. We have two primary weak layers that we've been dealing with all year, at least the ones that I'll focus on for this talk. The picture is a bit more complex these days if you're reading the forecast, but these are the two widespread weak layers that we've been talking about quite frequently throughout the season. So we'll dive right in now to some of the topics that we've focused on in the forecast, one of which, unfortunately for us, due to these two weak layers, has been remote triggering. So I'll start each of these sections with just a basic, a little bit of a basic definition, and then I'll work our way into a little bit deeper concepts with each. So remote triggering of an avalanche, what does that actually mean? I think there's a bit of misunderstanding out there. It's not, pressing a button on a remote and making an avalanche go off, as cool as that would be. It's when an avalanche releases some distance away from the trigger point. So when we talk about triggers or trigger points, we need either a person, an elk, an overburden of snow, something to physically collapse the weak layer, and that is the trigger. And the area that they do that on or in is the trigger point. So when you remote trigger something, you can literally cause an avalanche some distance away from you. You don't need to be on the avalanche to trigger the avalanche. When conditions are promoting remote triggering of avalanches, they're particularly sketchy, and choosing safer terrain and ski lines to ride can be very, very difficult under these conditions. This video here is a remotely triggered avalanche. So again, triggered from a distance that Ben triggered in the Pioneer Mountains. He was on an off-duty day, kind of walking along a ridge line, expecting this sort of avalanche to occur. So luckily he had his camera at the ready, and I'll show you the video here. I could embarrass him a little bit by playing the audio of what he was actually listening to when this occurred, but I'll let your guys' minds wander on what that might have been. As you can see, that avalanche raced down the track and then just blow through the trees at the bottom. Ben could hear trees snapping. It was a large and destructive avalanche, certainly something you wouldn't want to tangle with. And again, this was triggered remotely. So he was in a safe location, flat terrain from above the slope that avalanched. This video here is one of the more remarkable ones I think I've seen this season, and it really depicts a lot of what I want to touch on today. So we'll play this video, and then I'll show you some screenshots that I think are interesting from it as we kind of move our way through the presentation. This is a skier triggered avalanche from early January in Highlight Canyon, south of Bozeman. As you can see, the skier enters the slope here. Looks like making some really nice ski turns. And then as he approaches the bottom of the slope, you can see that he releases a persistent slab avalanche that breaks quite widely all the way across the bowl and up onto the adjacent ridge. Just a fantastic video, one that we'll touch on more as we continue. So when we're talking about remote triggering, it's kind of a multi-step process. So I thought I'd break it down for you just a little bit further. First, we need a persistent weak layer, and that's usually we need a persistent weak layer. You can remote trigger avalanches on non-persistent grain forms, but it's far more likely if you're dealing with a persistent slab avalanche problem. If you want to learn more about the persistent weak layers and persistent slab and deep persistent slab problems that we've been dealing with in particular, throughout the season, you should check out Scott's last Digging Deeper presentation, which should be up on our YouTube channel any day now. He goes into a lot more detail about these problems and the history of them within our snowpack this season. So I highly recommend you going back and watching that. The second thing that we need is we need a trigger point, and we'll break down some common trigger points and why they exist here in a second. At that trigger point, the snowpack collapses. So the stiffer slab of snow that sits above the weak layer actually drops into the snowpack, collapsing that weak layer. When that happens, it needs to propagate a crack over a wider area in order to create the slab that, well, in order to release the slab, I should say, that comes down with the avalanche. And then, of course, you need steeper terrain for that to actually slide. So trigger points. The basic definition of a trigger point is just the area where a trigger initiates an avalanche. And as I mentioned earlier, that trigger can be us. That's what we're primarily concerned with. But it could also be a natural trigger, like a cornice fall, or just overburden from a lot of wind loading onto a steep wind loaded slope. It could be literally an elk crossing an avalanche path. There are a number of things that could serve as triggers. Some of the common trigger points that we see out there are around cornices. So these are going to show pictures as well as a little diagram in the lower left here that's going to show you kind of a side view of what the snowpack might look like near that trigger point. So there's that picture of the cornice in the lower left. As you can see right at the toe of the cornice, or the root of the cornice there, the snowpack layers get really thin. So there's a couple reasons why cornices or regions around cornices can provide trigger points. One is that the snowpack is going to be a bit thinner there than in other areas. So you're more readily able to impact the weak layer, because we're going to assume for this talk on trigger points that we already have a well-established persistent weak layer like we currently do out in the hills right now. And then also you're going to have more overburden from recent storm loading, from snow kind of spinning off the top of that cornice and loading the slope further down. So you're going to have added stress on the steeper portion of the slope. This is a picture from the 4th of July creek drainage in the White Cloud Mountains. And on the lower left-hand side of the image, you can see a large chunk that has come off of that cornice. And this avalanche was cornice triggered, another picture that Ben took from last January. And again, you can kind of imagine the snowpack getting thinner as it gets up closer to the cornice there. That cornice provided a big trigger, that big drop of a heavy load of snow right onto the snowpack, started that avalanche, and then it stepped down to a weak layer closer to the ground. Below rocks is another common trigger point for avalanches for very similar reasons to the cornice. The snowpack can get thinner there, and especially in our Sawtooth Mountains, you can get this kind of spin drift or snow trickling down during wind events or heavy storm events that starts to build up a thicker slab below the edge of where the rock meets the snowpack, and adding stress to those particular weak layers. Objects that protrude out of the snow can be a trigger point as well. Again, the snowpack here can be thinner, and it'll kind of concentrate stress around these trees or rocks that are sticking up through the snowpack. In this image here, you can see that crown, and oftentimes if you take a close look at different avalanches, you'll see that those crowns kind of jump sometimes from these thinner sections or weaker points around trees, from tree to tree as it goes across the slope. Another common one are shallow snow over a protruding object. So this is one that is one that we talk about quite often in our region, which is kind of rocks or big craggy terrain where you can imagine, you can see some of the rocks in this photo, but only some of them were unveiled after the avalanche had occurred. So particularly there's a rock right in the middle of this bed surface. There's a rock off to the left where that skier track comes in. And those rocks can be very shallowly buried underneath the snowpack. And if the weak layer rides up and over those protruding objects, then the weak layer itself is also much closer to the surface of the snowpack. And again, one of those common trigger points that we're talking about are areas where the snowpack is thinner. It doesn't mean that the entire snowpack needs to be thinner necessarily, but it can be thinner locally at a given point, whether it's over a cliff band, stumps and logs, or most commonly rocks. Jumping back to our example of that highlight skier triggered slide that I showed you the video of earlier, this is standing down just beyond the run out of that avalanche and looking up at the crown. I think it's a pretty striking image from below. It looks a lot bigger than it did from the top. But you can see again, starting kind of in the left-hand side, these crowns kind of shoot from rock to rock to rock to rock all across the slope. And they failed there for a reason, and that's because the snowpack happened to be locally weaker there. And it also was a steeper roll, which that convexity started to concentrate some of the stresses in the weak or in that snowpack and create weak spots where it rolled over. Another example here of where the snowpack might be thinner could be due to wind loading. So you can imagine in this scenario, the wind kind of blowing or scouring some of the snow from right and depositing it off to the left. And you can see how that slab tapers as it moves from right to left across the image. So the skier came down here, triggered an avalanche where the snowpack was thinner, which happened to be over these rocks. It was probably a little bit scoured from wind during the event, and then propagated out into a deeper snowpack. Really cool photo that Scott sent me just prior to the presentation came from Big Sky Ski Patrol. And this is one of the more unique looking crowns I think I've ever seen. But really cool how it kind of wrapped its way around that protruding rock there on the left-hand side. You can see that also part of the crown here followed this rock band, but I'm not sure I've ever seen a crown quite wrap around like that. So moral of the story here really is that, thinner spots, which can be formed either by wind scouring, thinning out the snowpack, rocks or things below the snowpack, or things protruding from the snowpack like cliff band or trees can really act as points where you're more likely to trigger an avalanche, or where crowns of avalanches tend to preferentially connect the dots. To give you another illustration of that, here's two different snow pits dug, assessing the same weak layer. I'm on the left here. That was February 17th from Galena Summit, and Chris is on the right, February 12th out in Frenchman's. And a thick and thin portion of the snowpack can be a local phenomenon, like I was mentioning, with some sort of a buried object like a rock, or it could be a bit broader scale. So these 2 points are only about 7 miles apart, and you can see the big differences in the results that you'll see in these two different tests. You can see my extended column test failed there. The snowpack is quite a bit thinner, and that weak layer is a lot closer to the surface, which gives us a lot better chance of triggering that with our weight of either our sleds or our skis. To contrast that, again, we have a weak snow layer, the same one, the December 11th facets that Chris was testing there. But the main difference is going to be that this slab was upwards of 4 foot thick and mine was about 1.5 foot thick. And the likelihood of triggering this avalanche, at least in the location where Chris was currently at digging that snow pit, is a lot less likely. But you can see that the weak layer is still down there and still showing that it can propagate. Now we could change the whole picture for Chris there if we put him up in more wind-loaded, scoured terrain, and some of that uniform snowpack that he's testing there might be spread thin in a location. So that's really the difference in terrain that would probably be required to up your odds of triggering an avalanche in his situation. Whereas in mine, the odds that you could trigger an avalanche in a large portion of the terrain are pretty high. So the next thing we'll talk about is the actual collapse or the WUMF. So I think a lot of people have thought maybe they've heard of WUMF, but I think the best way to actually know is to experience one. It's a pretty unmistakable phenomenon. And the term WUMF has actually been adopted as a fairly scientific term. It stems from the sound of air essentially escaping the snowpack, or the sound of kind of the slab that sits above the weak layer crushing the weak layer, and then the air escaping. And that's kind of a whoomph sound. When the fracture of a lower snow layer causes an upper layer to fall, is the definition of a collapse. So to kind of see that in a little diagram here, you throw a skier or a snowboarder onto a slope, force that they apply can sometimes be enough to collapse that weak layer. I'll play this video again. And that's what we're talking about when we actually talk about a collapse. So in this depiction, this gray layer is the slab, the thicker, stronger portion of the snowpack. This kind of hash mark layer that gets crushed here is the weak layer. So we can imagine that as being our December 11th facets or January 27th facets and surface soar. And when conditions are ripe for triggering avalanches, you'll feel a lot of whumps as you're going. Well, oftentimes you'll feel a lot of whumps as you're going through terrain. And that's really a big red flag that says there's a weak layer, there's a slab sitting on it, and it doesn't take very much weight to cause that weak layer to collapse. The next ingredient that you need is propagation. And propagation is the spontaneous spreading of a crack within the snowpack without the addition of any external force. So once we have fractured that weak layer of snow beneath our feet, that crack once that fracture initiates, it continues through that weak layer underneath the slab, and that's the propagation. And if it propagates to some distance over to steeper terrain, it can cause an avalanche. One cool video that kind of demonstrates some propagation. This is a non-standard snowpack test that Ben and I performed in the boulders. I think it was maybe 2 years ago or 3 years ago now. But what Ben's doing in this video is he's running a saw through the weak layer. So essentially he is forming that collapse of the weak layer as he's destroying the weak layer with his saw. Up to a certain point, that weak layer then starts to spontaneously propagate a crack to the end of the column, which you'll see right here. So a really cool video that just shows that when he first started running his saw through that weak layer, he had only gone maybe 10, 15 centimeters into that second part of the slab where I started the video. And then that crack shot and propagated through the weak layer to the end of the slab. Some other examples of propagation, and this is where I really hope a lot of you guys start to have a bit of an aha moment when we're talking about remote triggering and what it can really mean when you're looking at it in real life scenarios on the ground with avalanches. This image was sent to us by Sun Valley Heli Ski. They experienced numerous remotely triggered avalanches in about a week's span. This is just the first one. But this collapse propagated through the weak layer all the way across the bowl and triggered the avalanche in the steep wind-loaded terrain on the far left side of the image, which was 800 to 1,000 feet away. So the approximate trigger location there is shown on the upper right as the skiers came down the slope, and the avalanche released on the entire other side of the bowl. So really remarkable propagation. And it shows that, you don't need just a plain or a planar open slope without cliffs or without rocks or without other things kind of protrusions sticking out of it like trees. This collapse was able to propagate all the way across this slope. So pretty remarkable. Here's another photo from where the skiers then stopped on the ridge, looking back across. And then just 5 days later, they reported several more remotely triggered avalanches. These ones, actually, there were 3 different, and they were 3 to 6 feet deep, and they were occurring as the Sun Valley Heli-Ski landed their aircraft in some of their safe pickup and drop-off locations. And these avalanches were releasing upwards of a quarter mile away, which is pretty hard to fathom when you start thinking about it. I think that a lot of people, when we talk about remote triggering, might think more on the lines of what Ben was experiencing in that Pioneers video, where you could be on top of the ridge, the avalanche could be triggered just below you. But these examples show that you can trigger avalanches from a very great distance away. And then, of course, that can take out a majority or all of the bowl that you're standing in and then run far into the flats below. This is another remotely triggered avalanche from this season. This is from January 17th, and it was remotely triggered by riders in Pole Creek. And it was the 4th rider who had crossed under the steeper slope above. And when they came back through, this debris was sitting on that track where they had crossed under earlier in the day. So another misnomer that I think people get confused with sometimes is that if you're on, let's say, either an established skin track or some sort of a snowmobile trail or something similar to this in Pole Creek where multiple riders or skiers have already crossed, that somehow it's safer than if nobody had crossed it. And the reality of the situation is that we have numerous examples of people being the 3rd, 4th, 5th, 9th person to cross a particular slope or to cross a particular part of the skin track before the skin track or before that weak layer underneath them gives way and it avalanches. So if you think about this example I'm showing you right here, the weak layer is buried somewhere below what you can see in this photo. So even though there are tracks, you might be disturbing the surface snow, maybe the 6 to 10 inches of snow that fell the night prior. You're not really doing much to the weak layer that's buried deeper down in the snowpack, like in those videos that I showed you of myself and Chris. So it could be that the 4th rider just happened to find the one spot, or maybe a group of riders happened to sit, and that added weight was enough to collapse that weak layer, even below an established skin track or snowmobile trail. Unfortunately, one of the first avalanche fatalities that I had to deal with in my career was one where a couple of snowshoers actually were crossing on an established skin track, and it was the third snowshoer that happened to have a huge pack full of climbing gear, and he was a heavier, larger male, and the 2 individuals that had crossed before him were smaller females, and he just happened to have enough weight to be the one on that same path that the other 2 had crossed to trigger the slide. One remote trigger that I dealt with locally here that I have experience with was out on Morgan Ridge, which is in Trail Creek, just to the east of Sun Valley. And these slides were triggered from almost a quarter mile away down the ridge. So I've marked the trigger point there in red. And as I was walking out the ridge, I heard just a really loud collapse and then just saw a ripping crack go out in front of me. So I reached down to grab my camera to take a picture of the crack. And when I looked up, I was actually looking up into the bowl about a quarter mile away to see this avalanche that had released in steeper terrain. So when you're working with a really well-developed weak layer like these, some pretty remarkable things can happen. And I think it behooves us all to kind of expand our definition of what's safe terrain, what's connected terrain, and open our eyes to the realities of how wide and far propagation can occur and avalanches can release. So that brings us into our next little focus topic, which is connected slopes. Slope steepness is one of the most important terrain factors that you guys can focus on when you're out there selecting safe slopes to ride. Most avalanches will occur anywhere from 30 to 45 degrees. But when remote triggering is on the table, avalanches can be triggered from low angle or even flat terrain outside of where the actual avalanche initiates. And that's what we're talking about when we're talking about connected slopes. So here in this image, we have the gray blob in the center, which is where the avalanche is most likely to occur. So that's where the start zone of this particular path is most likely and most common to occur. It's, right in those sweet angles of 35 to 45 degrees. But let's say that you established your skin track on this slope and you were working your way up from the bottom and you were coming out of these trees until you got to this gentler terrain out here, which could be just on the brink of avalanche terrain or maybe even just under. If you happen to collapse a weak layer that's in this gentler terrain, say you were right here, and that weak layer then propagated outward around you, you might get away with it if it did something like this. You might feel a collapse underneath your feet, and then you can see it spread out from you in all directions. Sometimes when you have a really violent collapse like that, you can see it shake trees or bushes and knock the snow off of trees as it goes through, say, those willows in that photo there. But if it continues and it gets out into this start zone of this avalanche path, a couple of things can happen. One is just that gray blob could then avalanche and go down into that defined path. But maybe something a little bit worse could happen, which is the fact that once the avalanche begins to fail in that avalanche start zone, it might pull out all of the connected terrain that it happens to be steep enough, if the slab is strong enough, to pull it all down together, which an avalanche of that sort could pull out all of the blue area as well. So you could collapse a weak layer, have it propagate to a steeper slope, have that start to slide, and then see an avalanche spread to lower angle terrain. So when we talk about connected terrain, that's what we're talking about. You want to be thinking about what's to the side of you, what's above you, things like that. It gets way, way more complicated when you're in complex terrain with multiple avalanche paths, and it gets way, way more complicated when we're talking about a very touchy, persistent weak layer that can propagate, as we saw from those slides from Sun Valley Heli-Ski, upwards of a quarter mile across an entire bowl. Back to our photo here from outside of Bozeman, Highlight Canyon. And you can see that not only do we have this avalanche that we have to deal with, excuse me, so we're talking a little bit about slope angles here. That skier was able in this example to ski through avalanche terrain without actually triggering the avalanche. And the question isn't was the slope steep enough? We know that it was, but more so, how did he make it all the way through that avalanche terrain without triggering that avalanche? Well, he started off in kind of 32-degree terrain, which might be fairly stubborn to trigger an avalanche, passed through the money zone kind of close to 35 degrees, but maybe just didn't hit the quite right spot. Maybe the slab was just a little bit too thick for him to impact the weak layer. And then he kind of made it out of primetime avalanche terrain all the way down into lower angle slopes at the bottom, which is where that avalanche was actually triggered. So when we talk about avalanche terrain, I think we need, particularly when we're talking about persistent weak layers, we need to be thinking about not only where the avalanche initiates, but where the terrain is that you're connected to traditional avalanche terrain, slopes steeper than about 35 degrees that might be above you. This is that same avalanche, but kind of a view from across the basin there. The avalanche that we've been showing you pictures of so far is on the right-hand side. And what also happened when this slide occurred is that it sympathetically released a second avalanche on the other side of the ridge. So when we talk about a sympathetic avalanche or a sympathetic trigger, that's when one avalanche triggers another avalanche just some distance away. And the second slide release is due to the disturbance of the first. So in one sense, you can kind of think about it as the force of the first avalanche coming down, remotely triggering a second avalanche. So in order for that to happen, some sort of a collapse in the weak layer needs to span from one side to the other to release that other avalanche. So the last main topic that we'll get into are avalanche or so-called safe zones. And I think this is going to be a fairly short section because I really want to add some skepticism into your guys' thought processes when you're thinking about what is a safe zone. So a safe zone is really just an area that you're less likely to be caught in an avalanche. So it's generally talked about when people are talking about where they think is a safer zone to regroup. Some generally safer zones might be well beyond the run out of the avalanche path, a flat ridge top with no hazard from above that's also well back from the ridge, or some low angle slope that doesn't have avalanche threat from above. I think calling these more along the line of safer zones, or as Chris told me in a conversation a couple of days ago that I thought was pretty apt, was safe enough zones, given the avalanche problem, is probably a little bit more accurate. And really the long story short is that it's all pinned to what type of avalanche problem you're exposing yourself to. And you need to think about that critically. And hopefully some of the examples that I've shown you throughout this presentation so far have kind of opened your eyes into what is truly might be a safe zone when you're talking about an avalanche that can span the entire basin. This is a pretty shocking video that I found of a skier triggered avalanche in France. And I think it highlights something that I want to point out again about safe zones. We'll pause it right here. And some of the backstory is that these skiers were coming down this slope, and a bunch of them had decided to kind of go down a little bit further and then tuck themselves under this rock, assuming that for their purpose for this particular day, it was a safer zone to hang out.
We'll go.
I had to mute it there because there's some expletives, but you get the picture. There were 6 people in the group, 5 were caught, 3 were partially buried, and 2 were shallowly buried under about 30 centimeters of snow. Again, this avalanche occurred when the 5th person, so you can count the 4 down there underneath, and then the 5th person, using the same entrance track in all 5 cases, crossed out onto the slope. What you can also see is that it propagated very widely off to the right, and that fracture propagated downslope some distance and then released in that pocket down in the bottom left hand before then pulling out the majority of the terrain all around them. Thankfully, 3 people were injured and 1 person spent several days in the hospital, but everybody survived this avalanche. I think that this is a really important example, and one that I've kind of looked back on some of my previous terrain selections in the past and kind of had to look critically and thought to myself, was I really in a safe zone when when I was exposing myself to that avalanche terrain? I think this quote right here from Blaze Reardon, who's a former forecaster for the Sawtooth Avalanche, speaks to that. It's particularly hard to find true safe zones in complex terrain with multiple start zones and undefined tracks and runouts. Tucking behind a few scraggly trees or a boulder isn't enough. And when I read that quote, it really makes me think critically about some of the choices I've made, where you have this idea in your head that you should be trying to keep some your ski party within view as you're managing terrain. But you have to balance that risk of them skiing, the full length of the run with the risk of, what kind of terrain you're exposing both of you to keep yourselves within view. I can probably think a number of occasions where I had that idea where, well, at least I'll tuck behind this tree and hang on, or I'll get around this cliff band and hang out there. But in hindsight, those decisions were pretty foolish. And having a better understanding of how wide avalanches can break really kind of has helped me decide where I actually think a safe zone is or isn't in the years to follow. So coming back to our skier triggered slide in Bozeman, or south of Bozeman in Highlight Canyon again, I've taken a screen grab of where this skier actually triggered the slide, and it might have been a half turn prior to this. But if you look closely in this image here, you can see where the slab has fractured right here. And you can see this crack kind of extending all the way out here. And the process of collapse and then propagation can happen in a fraction of a second. So again, we're way down into lower angle terrain. He collapsed the weak layer here. It shot back up the slope and then took out the slope that he was just skiing and riding on. When we're using this to talk about safe zones, I think that it's pretty interesting to, let me clear my drawing here. I think it's pretty interesting to look at where the skin track is. So I'm not 100% positive, but it seems quite likely that that was the skin track that they put in, that then came up this treed slope and around before they decided to ski this bowl. And when you look at that, you like to think that where you put your skin track is one of the safest places, but then you skip forward into the next picture and you can see that the run out of this avalanche pretty clearly would have been bad news had you been on the skin track. And remember, the skier was only about here. So the distance between the actual skin track and where he was when he triggered the slide really wasn't that far. So it seems quite reasonable that somebody, could have thought to bring the skin track, 30 feet closer to the toe of that avalanche, and avalanche or debris closer to where that skier had triggered it. And if that skin track had been put just a small distance closer, it seems fairly likely that they could have triggered that slide while ascending the slope, which would have been pretty bad news. So one thing that you can do when you're, or at least I think this is, I anticipate this coming up as a question, so I'll just address it because I figure it'll come up, is the alpha angle. And the alpha angle is essentially the angle between horizontal and a line drawn from the highest point of the crown face to the toe of the debris, And these two angles here, 19 degrees and 22 degrees, are where, the 100-year event avalanche might run to. So it's going to run into fairly flat terrain with an alpha angle. Again, it's that angle between the horizontal and this line to the top of the avalanche path. That's about how far statistically some of those avalanches would run in a historical 100-year avalanche. Is this a good thing to think about while you're out in the mountains? I think yes. I mean, why not? If you're going to pass by a well-defined single avalanche path and you're wanting to give yourself an extra wide buffer, then the alpha angle can be a very useful tool. But in reality, we're operating in complex terrain with unknown numbers of avalanche paths. We often can't see the start zones to make accurate measurements. It's really hard for us to judge the runouts if we don't have a well-defined, well-documented avalanche path to sample from. So, this is mainly used in kind of structural engineering or building roads and things like that when you're thinking about it on that scale. I mean, maybe if you were going into a hut trip into a big alpine basin, you wanted to kind of take some measurements all around you, figure out where maybe the safest spot furthest from the avalanche path might be. It might be handy, but in real life, it's kind of a fun thing to measure and think about. And if you have a well-defined path, go ahead and use it, but understand that you shouldn't be relying on it wholly. But it is an interesting thing to consider. So some parting thoughts. I hope some of these images and videos can kind of help us rethink what's possible when we think about dangerous, widespread, persistent weak layers buried in the snowpack. This video right here, I think, kind of speaks for itself, but it was this season out in Colorado. How widely avalanches can propagate with very persistent weak layers is pretty phenomenal. The type of terrain that it can cross, like jumping over areas like this, for instance, is also really remarkable. Let me start that video again here. And then also looking at a slide like this, you start to realize, wow, it's overrunning, very gentle looking, approachable slopes on the far, far left hand of that video over there. Going into terrain that I think a lot of us prior to this talk, and hopefully not as many of us after this talk, might have considered to be fairly safe terrain. This slide was triggered remotely from where the skiers are standing. So I kind of want to leave you with a few tidbits. First, know the problem. Persistent slab and deep persistent slab avalanches behave differently than storm slabs and wind slabs. They can be triggered weeks and months after a storm, and avalanches can propagate widely, spanning multiple sub-ridges at a time. So what can you do? Well, the simplest thing to do for you to learn about when these conditions exist is to check the forecast. Secondarily, you can talk to each other, talk to us, send in your observations. If you're getting remote triggered avalanches, collapsing and cracking, things of that nature, we want to know. Persistent slab avalanches are dangerous beasts, and the more information we can get out there, the better. So look it up. Long story short is remote trigger avalanches equal a very unstable snowpack. Second is to not lean on familiarity, particularly when we're dealing with persistent weak layers. So this avalanche, or this particular weak layer that we're dealing with right now, might be a once in a decade weak layer. So what does your experience really tell you if you've been skiing here for 15 years? You might not have actually seen an avalanche in that terrain during that 15 years, but your sample size is pretty dang small, especially if it's only going to occur once on a given day within those 15 years. Ian McCammon's paper describes familiarity as parties traveling in familiar terrain make riskier decisions than parties traveling in unfamiliar terrain. And that effect is pronounced even more for parties with substantial experience and training. So because you've been there before, because you've skied that slope before, really kind of goes out the window if you're being honest with yourself. So what can you do about familiarity and the problem of familiarity? I just suggest that you show some humility. Expand your mind to the possibilities of persistent slab avalanches and their consequences, and be honest with yourself and your experience in that given terrain. The next thing that I want to touch on is to choose safe up tracks. It's been really kind of heartbreaking to see the rash of avalanche fatalities, particularly in February. And an alarming number of them have involved people on the up track, which is really easily the worst possible place you can be when you trigger an avalanche. So you're in tour mode, your skis aren't going to release, you can't move very quickly, you don't really have any chance to escape the avalanche. You have way more snow above your head. You can go on and on. There's just a lot more reasons that you just don't want to be in an avalanche when you're on the up track. So what can you do? Imagine an avalanche in the terrain you're in. So even though it's an established skin track, are you in the run out? Are you there because it's the safest way or the easiest? Back to the example I shared with you about that fatality, which happened in Colorado, that snowshoer who was the third to cross, the two in front of them and the fellow that was killed had a conversation before they crossed that particular avalanche path, and they didn't want to go that close to the toe of the avalanche slope. And they knew that the safer route was actually going to be in the valley bottom, but it took them through willows. And I don't know if you've ever tried to walk through loose facets in willows, particularly in snowshoes, but it's a pretty gnarly event. You're basically climbing your way through them. And they determined that it was going to be a bigger deal and a longer ordeal to have to take the safer route rather than take the established skin track. Lastly, I want to encourage people to realize that we're really not done yet. We're likely to see at least a few more big storms. And as the sun and temperatures climb, we'll add another test to these persistent weak layers, which is meltwater. But that is another digging deeper topic altogether. And thankfully, it's one that we'll hopefully have the privilege to have Simon Troutman deliver, the one after Ben's in late March, and he'll be talking about wet snow avalanches. So I'll save you from going down that rabbit hole until we get there later in March. I'll let Simon take you there. But until then, I hope you all enjoy the sunshine, find some safe skiing and riding along the way. And thanks for joining me this evening, and I'll take any questions.
Great, thanks, Ethan. That was really, really informative. We've got quite a few questions starting to come in for the Q&A, so I'll just start firing away for you. For other people who have questions, feel free to type those in the Q&A box or hit the raise hand feature. And while we've got Ethan here ready to answer any question, we might as well fire away at him. So the first question from Leo is, have you skied sustained avalanche terrain this year since the weak layer was buried?
No, I haven't. And I can speak personally that the reason really would be that I just can't trust it yet. And internal conversations with the avalanche forecasters, the amount of terrain that you could choose to safely ski with very low likelihood of avalanching is pretty uncertain, and it's a pretty small sliver. So when we have buried weak layers like these, you really are rolling the dice to some extent. It's hard to say how much. As we get further and further away from a storm, it's a lot harder decision to make to avoid avalanche terrain. But what hasn't changed is the fact that those weak layers still exist. They're still down there. And as long as they're down there, the odds of triggering an avalanche remain.
So Scott touched on this a little bit, talking about the deep persistent slab avalanches going into the spring at the last digging deeper, but could you elaborate a little bit on what remote triggering and safe zones could look like with that deep persistent slab as we go into the last few months of winter? And so to complicate the question more, as the forecast is coming out as moderate, for you, how does that change your mindset at all, or what's your outlook on that?
Yeah, so the question's really just, how does it change terrain selection as the danger goes down, essentially? Is that?
Yeah, as the avalanche danger rating goes down, but that deep persistent slab weak layer is still in there. And you just said you don't trust it yet. How is that changing your mindset going out into the mountains?
It's really just a process of likelihood. So, as the danger goes down, that's reflecting that there are less places that we feel that you'd trigger an avalanche like that. but it doesn't mean that there are no places that you can trigger an avalanche like that. So yeah, it's really just a game of likelihood.
Okay. All right, Dirk's question, what effect will rain have?
Yeah, that hopefully Simon is going to touch on in greater detail in a couple weeks, but hopefully it hasn't all happened before then. But yeah, when rain comes, it's going to percolate down to that weak layer, and my assumption is that it's really not going to behave well, particularly that December 11th weak layer that's near the ground. So when that rain percolates down, it kind of hits that weak layer and then spreads horizontally. And rather than overloading the weak layer and crushing it or fracturing it, we're essentially liquefying it as that water spreads out horizontally along the weak layer. And once you've disrupted enough of that weak layer, it's going to lubricate the bed surface enough to just allow the wet slab avalanche to come down. So I'd expect that there will be some very interesting wet slabs come spring.
Great. We'll follow up that one with a question from Ed. In the early season and the snowpack is thin and you have widespread collapsing and warming of the weak layer, does that have any impact? Does that have any impact on the snowpack later in the year? And does it heal?
That's a great question, Ed. And you know, speaking to this particular weak layer, December 11th, we've seen multiple repeat avalanches on the same weak layer. So it can be something that was buried, not only warmed, but slid. And then we've seen avalanche, subsequent snowfall reload onto that same weak layer and cause more avalanches. So similarly, you can have collapses occurring multiple times in a similar area. So it can't hurt it. It probably does make it slightly better, but it certainly doesn't mean that it has gone away. Another example is that we can go to a slope that already has collapsed, and we know it has because it's avalanched, and then we do snowpack tests nearby, and we find that we're still getting propagating results and collapses in those snowpack tests.
Great. So now we have a question about the Bozeman video from Sam. So this one's a little bit longer. I'll just read it to make sure I get it correct. So is it at all possible that that in the Bozeman video, the trigger was higher and just a bit time delayed? Or in other words, could it take several seconds or even many seconds for the initial collapse to occur or for the propagation to actually spread the distance? He's asking, could you please show the original video?
Does he want to see the original video because it was bad quality or something when it was being played? Is that the... Or does he just want to see it again?
If it's easy, maybe play it again and then I can read that question again.
Yeah. Yeah, so to answer that question though, the propagation occurs very, very, very fast. So the time, for instance, the time delay between when I triggered that crack on Morgan Ridge and the avalanche occurred was a matter of seconds. It was to go a quarter mile. This is only, a few hundred feet or maybe a few hundred yards up the slope. So that could happen in a fraction of a second or a few seconds. So it did appear that it was triggered from lower on the slope, or maybe a half turn faster than the screenshot that I grabbed. This is the video here.
And Ethan, I'll add in, I see a good note from Scott here saying that Ron Simois, if I got his name correct, he's a forecaster in Colorado, and he's done some work on crack and fracture speeds using videos to determine speeds. So that could be something to look into if, Sam, if you're interested in looking more at that.
Let me share my screen again here. Can you see that video again?
Yeah.
Yeah, it's remarkable how fast propagation of a crack can occur.
I could see the video is a little bit jolty, so that might add to the having it be harder to see. But we can certainly post this on social media and have it be smoother with a little context.
I did see a comment come up about what the failure layer was or something along those lines. I read really quickly, but the Gallup National Forest Avalanche Center did go up and check this out a couple days later and determined that it was a layer of facets below that slab. So it was a persistent weak layer. And remember that sympathetically released avalanche occurred on the right side, right where it's looking at right there, over that ridge in a bowl adjacent to this slide.
Thanks for replaying that.
Mhm.
All right. If anyone else has more questions, we can keep it going for a few more minutes and type them in the Q&A box. Okay. Well, I think that might be it. Really thorough presentation. Thanks, Ethan.
There you go.
Oh, one more. Oh, Sam saying thank you. So thanks for pulling that back up. And as I'm wrapping this up, if anyone has final questions, we can squeak a few more in. But we just a reminder to join the next Digging Deeper series on March 17th with Ben Vanden Boss, and he'll be talking about expertise and mindset. And another thank you to Josh and Parker as the observers of the year from last winter. You can still take that spot of observer of the year and simply just submit observations through the rest of this winter. And the last one is that the social media challenge for avalanche rescue practice is running through March, and we've got some great prizes donated from companies, and just hope to encourage folks to get out and practice avalanche rescue throughout the last part of the season, kind of that last run syndrome. We just want to keep the practice going throughout the season, not just at the beginning. So help us spread the word of practicing avalanche rescue by posting a photo or video of you and your backcountry partners practicing avalanche rescue on social media. Tag Sawtooth Avi, and we will draw names out of a hat for some great prizes. All right. Well, thanks again, Ethan, and thanks everyone for tuning in. We will update you all on the next presentations and events through social media and on the website. So enjoy the sunshine, and we will see you next time.
Thanks, guys.